Particle in a potential box of one dimension. One of the significant applications of the Schrodinger's wave equation is obtaining the energies and wave functions of the electron confined to move in a potential box. Now, a potential box can be understood in the context of a free electron in a metallic crystal. So, we know that metallic crystals possess a high concentration of free electrons, due to which these metallic crystals exhibit a high thermal and electrical conductivities. But the free electron in a metallic crystal freely wanders throughout the crystal lattice but never leaves the metal surface. This is because on the surface of the metallic crystal, the electron experiences an infinite potential barrier. This barrier in 3 dimensions acts as a potential box for the free electron. Inside the potential box, the electron experiences zero potential, and therefore the total energy of the electron is purely kinetic. So inside the box, the potential energy of the electron is zero and the total energy is purely kinetic in form. So if you reduce the box, which is in 3 dimensions, to 1 dimension, it forms a well of infinite height but with finite width. That means now the particle is confined to move in a well of infinite height but of finite width. Let the width of the well be A units and the height of the well, which indicates the potential at the boundary of the well, that is infinite.
Start.
In the case of 3-dimensional box, the free electron possesses 3 degrees of freedom, and thereby the electron's position can be represented in terms of 3 spatial coordinates, that is x, y and z. But in the case of a 1-dimensional well, the electron possesses only 1 degree of freedom. Hence, the electron is confined to move only along one spatial direction, that is x direction, say.
Start.
Inside the well, when the electron is moving along this x direction, then when the electron encounters these rigid walls, an elastic collision happens between the electrons and these rigid walls. But the energy of the electron remains unchanged, and simply the electron reflects backward. That is, the matter wave of the electron reflects backwards. But even though the electron collides at the well, or the boundary of the well, there is no chance for the electron to penetrate or leak out of the well. Therefore, the probability of locating the electron outside of the well is always 0, whereas the probability of locating the electron inside the well at any interval of time is 1. Now the boundary conditions for the electron motion in the 1-dimensional potential well can be represented as V of x is equal to 0, that is 0 less than x less than a, that means it is inside the well, and V of x is equal to infinite for x less than or equal to 0 or x greater than or equal to a. Similarly, for the wave function, psi of x is equal to 0 for x less than or equal to 0 or x greater than or equal to a, that is outside the well, and psi of x is equal to 1 for 0 less than x less than a, that is inside the well. Therefore, the probability of locating the electron is always 1 inside the well, whereas the probability of locating the electron outside the well is 0. This can be understood from these boundary conditions. Now, to obtain the allowed energies of the electron and the wave functions for the electron, we have to solve the Schrodinger's time-independent form of equation. Now, Schrodinger's wave equation is the quantum mechanical equivalent of the Newton's second law in classical mechanics. We all know that. Always Schrodinger's equation gives the time evolution of a quantum state or of a quantum system. The Schrodinger's time independent form of equation in one dimension can be represented as d square psi by dx square plus 2m by h cross square into e minus v of psi is equal to 0. Now, for a free particle, like an electron which is trapped inside this potential well, this equation can be reduced as d square psi by dx square plus 2me by h cross square of psi is equal to 0. Since v is equal to 0 for the electron inside this potential well, and the total energy of the electron in the potential well is kinetic. Now, the total energy of the electron inside the potential well is totally kinetic, as said earlier. Now, this total energy can be represented as E is equal to p square by 2m, where p is the momentum of the electron and m is the mass of the electron. From de Broglie hypothesis and its representation, this momentum of the electron can be represented as p equal to h cross k, where k is the wave vector and h cross is the reduced Planck's constant h by 2 pi. Now, substituting this here, you can write that E is equal to h cross square k square by 2m. This implies that 2me by h cross square is equal to k square. Now let us consider this as equation 2 and this earlier Schrodinger's equation is equation 1. Now substituting 2 in 1, we get d square psi by dx square plus k square of psi is equal to 0. Now this Schrodinger's wave equation here appears to us in form of a second order differential equation, so it has two solutions. Usually the solutions of the differential equation can be taken as exponential. Therefore, we represent psi of, so the solution psi of x can be written as, say, e power alpha x, where alpha is a constant. So now d psi by dx is equal, psi of x is equal to e power alpha x. Now differentiating twice psi with respect to x, we get d square psi by dx square is equal to alpha square e power alpha x. Therefore, alpha square e power alpha x is plus k square into e power alpha x is equal to 0. This implies that alpha square plus k square of e power alpha x is equal to 0. Now, according to this equation, alpha square plus k square is taken to be 0, but not e power alpha x, because if e power alpha x becomes 0, it means psi of x becomes 0. Therefore, there is no existence of the electron inside the well. Electron may exist outside the well, which is impossible. Therefore, alpha square plus k square should be taken as 0. According to this, what we'll get? This implies that alpha square is equal to minus k square. This implies that alpha is equal to plus or minus ik. Now substituting this alpha equal to plus or minus e power ik in this expression, we can write the two solutions of the Schrodinger's wave equation as psi 1 of x is equal to a e power ikx and psi 2 of x is equal to b e power minus ikx. So these are two solutions of the Schrodinger's wave equation, and a and b are regarded as a constants. Now, by using the linear combination method, you can write a general solution for this Schrodinger's equation as a linear combination of these two functions psi 1 of x and psi 2 of x. That is, psi of x is equal to a e power ikx plus b e power minus ikx. This implies that psi of x is equal to a e power ikx is cos kx plus I sin kx plus b into cos kx minus I sin kx. Now psi of x can be written as cos kx into of a plus b plus sin kx of I sin kx into a minus b. This implies that psi of x is equal to a plus b into cos kx plus sin kx into plus I into a minus b into sin kx. This is how you can write. Now renaming the constants a plus b as a and I into a minus b as b. Now the wave function or the general solution of the Schrodinger's wave equation can be written as psi of x is equal to a cos kx plus b sin kx. Now this entire solution what I have written here is only for the understanding, but after writing this Schrodinger's equation, you can directly write the general solution, that is psi of x is equal to a cos kx plus b sin kx. This entire derivation is only an explanation for you. You can go to the expression directly. That is, the general solution of the Schrodinger's equation d square psi by dx square plus k square psi is equal to 0 is psi of x is equal to a cos kx plus b sin kx. Now the constants a and b can be obtained by applying the boundary conditions. Now applying the first boundary condition. The first boundary condition is psi of x is equal to 0 for x is equal to 0. This implies that a cos 0 plus b sin 0 equal to 0. So sin 0 is 0, cos 0 is 1. From this we get a equal to 0. This implies that now the wave function can be represented as psi of x is equal to b sin kx. Now imposing the second boundary condition, that is psi of x is equal to 0 for x is equal to a, that is at the boundary of the well, we get b sin ka equal to 0. Therefore here either of the two terms, b must be 0 or sin ka must be 0, but b cannot be 0 here, because if b becomes 0, psi of x becomes 0. So it becomes so the electron has no possibility of existence inside the well, which is impossible. Therefore the only possibility is sin ka should become equal to 0. This implies that sin ka is equal to sin n pi, where n is an integer, that is n equal to 1, 2, 3, so on, but n cannot be equal to 0. We will discuss this later. Therefore sin ka is equal to sin n pi, because sin integer times pi will become 0. From this expression we can write ka equal to n pi. This implies that k square a square is equal to n square pi square. This implies that k square is equal to n square pi square by a square. But what is k actually? it is 2me by h cross square is equal to n square pi square by a square. Now upon cross multiplication we get E is equal to n square pi square h cross square by 2ma square. Now we know that h cross is a reduced Planck's constant, that is h cross equal to h by 2 pi. Substituting this we get E is equal to n square h square by 8ma square. Observing this expression clearly, we can understand that the energy of the electron inside the potential well is not continuous, but it is quantized or discrete. That means electron in a potential well can possess only some allowed energy values which depend on a term known as n, which is the principal quantum number. Therefore, particle in the potential box, solving the equation of the particle in the potential box, we can understand the evolution of the principal quantum number. So the electron's energy inside the potential box is always quantized according to the quantization rule, n square h square by 8ml square. Now, as I said earlier, n should not be equal to 0. If n is equal to 0, it means the energy of the electron becomes here equal to 0. Energy is 0 means, as discussed earlier, the total energy of the electron is kinetic. Therefore, the momentum of the electron becomes 0. Momentum becomes 0 means it leads to a violation of Heisenberg's uncertainty principle. Therefore, n cannot be taken to be 0. It implies another point that an electron, even if it is in its lowest energy state also, should possess a non-zero value of energy. So an electron in a ground state also possesses a non-zero value of energy. It cannot be 0. Now if you represent the energy level diagram of the electron in the potential well, x equal to 0, x equal to a, these are the boundaries of the well where the potential is infinite. Now if you put n is equal to 1, if you take n equal to 1, so n equal to 1 is a principal quantum number that represents the ground state, that is n equal to 1. For n equal to 1, the corresponding energy of the electron is given by E1 is equal to h square by 8ma square. Now if the electron moves to the first excited state, this first excited state is designated by the principal quantum number as n equal to 2, and the corresponding energy is given by E2 is equal to 4h square by 8ma square, that is equal to 4E1. Similarly, if the electron moves to the second excited state, then the principal quantum number n becomes 3, so the corresponding energy is E3 is equal to 9E1, and for the third excited state n equal to 4, the energy becomes E4 is equal to 16E1, and so on. Therefore, if we write the ratios of energies, is given as E1 is to E2 is to E3 to so on is equal to 1 is to 4 is to 9 is to so on. This is how the energy of the electron can be in the potential well can be considered. So the energy of the electron inside the potential well increases in this manner as proportional to n square. Right. Now from this expression we can see that Ka equal to n pi here. Therefore, K becomes equal to n pi by A. So the electron's wave vector can be represented as n pi by A. Now substituting this in the wave function for the electron, that is psi of x equal to b sine kx, we get the allowed wave functions of the electron are given as psi of x is equal to b sine n pi x by A. That means if you put n equal to 1, we get the ground state of the electron. So in this ground state, the energy of the electron is h square by 8 ma square. If you put n equal to 2 here, it represents the first excited quantum state for the electron and the energy is 4 even. If you put n equal to 3, then we get the second excited quantum state for the electron where the energy is 9 even, and so on. So psi of x represents the various allowed quantum states for the electron to occupy. Now here B is the probability amplitude of this function. So this probability amplitude B value can be determined by applying the normalization condition for a probability. That is, according to the normalization condition for probability, we can write it as, because the width of the well is finite from 0 to a, that is integral 0 to a modulus of psi of x whole square dx is equal to 1. This is the normalization condition for probability for the particle in a potential well of finite width and infinite height. Now substituting the psi of x here, we'll get, this implies that integral 0 to a b square sine square n pi x by a dx is equal to 1. This implies that modulus of b square integral 0 to a sine square n pi x by a dx is equal to 1. Now this implies that modulus of b square integral 0 to a sine square n pi x by a dx is equal to 1. Now integral sine square x is nothing but 1 minus cos 2x by 2. So we can write this as modulus of b square by 2 into integral 0 to a 1 minus cos 2 n pi x by a of dx is equal to 1. Now applying the integration, now we get modulus of b square by 2. Applying this integration, what you get? If you substitute a here, upper limit, that is a, so a, so we get integral 1 dx is x. Substituting here, we get a minus, if you substitute x equal to a here, so what happens now? Integral of so okay, we'll do this integration. This implies that modulus of b square by 2, it becomes x minus sine of 2n pi x by a by 2n pi by a. These are the limits of integration 0 to a. Now this is how we integrate, because integral sine x, integral cos x becomes integral sine x. Integral cos ax is equal to sine ax by a. This is how we got it. So this implies that this is equal to 1. This implies modulus of b square by 2. So substituting here x equal to a, you get a minus. If you put x equal to a here, a get cancelled out. You get sine 2n pi. Sine 2n pi is 0. So again this term becomes 0 minus. If you put 0, the lower limit becomes 0 here for x. And now if you put here minus of minus, it becomes plus. If you put x equal to 0 here, sine 0 is 0, so everything becomes 0 is equal to 1. So this implies that modulus b square by 2 into a equal to 1. This implies that b is equal to root over 2 by a. Therefore, the allowed wave functions of the electron can be written as psi of x is equal to root over 2 by a into sine n pi x by a. So these are the allowed wave functions of the electron in the potential box, and this is the expression for allowed energies of the electron in the potential box. So this is equation 4 and 5. 4 indicates the allowed energies of the electron, and 5 indicates the expression for the allowed wave functions for the electron, or the allowed quantum states for the electron in the potential well. Now after this we have to find the probabilities. So if now the electron, say it is moving from one level to another level, or one quantum state to another quantum state, where is the probability of locating the electron? Maximum or 0 in between these 2 points, and in between the width of the well. In this width of the well, at what points the probability of locating the electron will be maximum or 0? You have to find it out. To find out, what you'll do is, first we'll take for ground state. For ground state, we know the ground state is indicated by the designated by the quantum number n equal to 1. So n equal to 1, now psi of x becomes psi 1 of x is equal to root over 2 by a into sine of pi x by a. Sine of pi x by a. Now x varies in between 0 to a. We know that the width of the well is finite, so x varies from 0 to a. So if x at x equal to 0 and x equal to a, that is the boundaries of the well, that is x equal to 0 and x equal to a, that is at the boundaries of the well, what happens is, if you put x equal to 0 here, we get psi 1 of x equal to 0. If you put x equal to a here, it becomes a gets cancelled, becomes sine pi is 0. So this implies that psi 1 of x becomes 0 at the boundary. So psi always vanishes at these boundaries. Psi vanishes at this boundary. So that means there is no probability of existence for the electron at the boundaries of the well. So psi vanishes at these points. So if psi vanishes at these points at the boundaries, then at what point is the probability of locating the electron maximum? When it is in the ground state. So that can be taken if at x equal to a by 2. If you put x equal to a by 2 here, we get sine pi by a into a by 2, a get cancelled, so we get sine pi by 2. Sine pi by 2 becomes 1. Therefore, psi 1 of x, psi 1 of a by 2 is equal to root over 2 by a. It is maximum. Therefore, when the electron is in the ground state, then there is a maximum probability of locating the electron at the center of the well or at the midpoint of the well, that is at a by 2. Whereas at the boundaries, psi vanishes. So maximum is at midpoint. So this is how you can represent the probability curve, where maximum is at the boundaries, at the midpoint. This is for the ground state. Imagine the electron is now moving to the first excited state, that is psi 2 of x. The quantum state is designated as psi 2 of x, and now the corresponding energy is E2, and the quantum number is n equal to 2. Now again for psi 2 of x, for first excited state, that is n equal to 2. Now psi 2 of x is equal to root over 2 by a into sine of 2 pi x by a. Now if you put x equal to 0, in this expression, if you put x equal to 0, at x equal to 0 and x equal to a, you put x equal to 0 here, it becomes a sine 0, 0. If you put x equal to a here, a gets cancelled, so sine 2 pi is 0. So psi vanishes again at the boundary. So psi 2 of x is equal to 0. This implies that even in this first excited state also, at the boundaries, there is no probability of locating the electron. So psi vanishes at the boundaries. Now, at what points will the probability of locating the electron to be maximum? We'll see that. Now, not only that, even if you put x equal to a by 2 also, you get psi 2 of x is equal to, put a by 2 here, a by 2, a gets cancelled, 2 gets cancelled, you get sine pi, so it is 0. So there is no probability of locating the electron even in the midpoint. that is at the center of the well. So at what point is the probability of locating the electron to be maximum? If you want to see that, go for at x equal to a by 4, means this is the point of a by 4 at this point. Because we put x equal to a by 4 here, a gets cancelled. Now 2 2's it goes, so sine pi by 2 is 1. So psi 2 of x is equal to root over 2 by a. Similarly, at x is equal to 3a by 4. 3a by 4 means exactly at this point. Now again, psi 2 of x is equal to 3a by 4. So a gets cancelled, 2 2's it goes. So sine 3 pi by 2, sine 3 pi by 2 is minus 1. So you get root over minus 2 pi by a. Therefore, the probability of locating the electron in the second excited state is maximum at a distance of a by 4 from the origin of the well and at a distance of 3a by 4 from the origin of the well. Therefore, these are the limits. So if you write this probability function, if you draw this probability function, it appears like this. So here the probability of locating the electron is maximum, that is a by 4. Here the probability of locating the electron is maximum, that is 3a by 4. Here and here it is maximum. But at these points, the probability is 0. In the second excited state, the first excited state. Now, for the second excited state, that is for n equal to 3, the corresponding wave function of the quantum state can be given as psi 3 of x is equal to root over 2 by a into sine of 3 pi x by a. Now, at x equal to 0 and x equal to a, that is at the boundaries, again psi 3 of x vanishes, because you know that if you put x equal to 0 here, it becomes sine 0 is 0. So psi vanishes at the boundaries of x and a, because similarly you put a here, a get now a here, now it becomes sine 3 pi is 0. That means psi vanishes at the boundaries. So there is no existence of the electron at the boundary of the well, even when the electron is in the second excited state with energy E3. Now, where is the probability of locating the electron maximum when the electron is in the second excited state? To learn about that, we'll put let x equal to L a by 6. Take x equal to a by 6. X equal to a by 6 means we put x equal to a by 6 here. A by 6, we get sine pi by 2. Sine pi by 2 is 1. Therefore, you get psi 3 of x is equal to root 2 by a. Similarly, if you put x equal to 3a by 6, that is a by 2, again we get psi 3 of x is equal to root over 2 by a into sine of 3 pi by a into 3a by 6. So we get again 3 pi by 2. Sine 3 pi by 2 is nothing but minus 1, so it becomes root over 2 by a. Now again at x equal to 5 pi by 6, we get psi 3 of x is equal to root over 2 by a into sine of 3 pi by a into 5 pi by 6. So again at x equal to 5a by 6, now we have psi 3 of x equal to root 2 by a into sine of 3 pi by a into 5a by 6. Now we get sine 5 pi by 2. Sine 5 pi by 2 is 1, so we get psi 3 of x as root over 2 pi a. Now if you plot the probability distribution curve, now for psi 3 of x we get a maximum at L by 6, that is equal to root over 2 by a, and at 3L by 6 we get this is another probability distribution curve where the psi vanishes at the boundaries, that is at x equal to 0 and x equal to a, where it is lying in the second excited state, and psi is maximum at L by 6. At a by 6 there is a position of x equal to a by 6 and x equal to 3a by 6 and also x equal to 5a by 6. And similarly for at x equal to L by 3, that is a by 3 and 2a by 3, again psi becomes a 0. So when the electron is in the second excited state, that is psi3 of x, the probability of locating the electron is maximum at x equal to a by 6, 3a by 6 and 5a by 6, but it is 0 at the boundaries and at distances a by 3 and 2a by 3 from the boundary of the well. Therefore, we can finally conclude that a particle confined to move in a potential well of infinite height, of infinite depth rather, in that case the particle occupies discrete allowed energy states. Psi 1 indicated by the wave functions psi 1, psi 2, psi 3, so on, and whose corresponding energies are E1, E2, E3 and so on. Now plotting the corresponding probability densities, we get like this. Now the particle is confined to move. Now if the particle is confined to move along the x directions at the well, the corresponding probability densities of locating the electron in various energy states can be represented like this. This is for the ground state, that is n equal to 1, and the wave function is psi of phi 1 of x. For the first excited state n equal to 2, the corresponding probability density appears in this manner, and for the second excited state, this is psi 2 of x. For the second excited state, n is the corresponding quantum number is n equal to 3, and the wave function is represented as psi 3 of x. Now it can be given by is represented as Thank you for watching the video.